In this video, I'm going to finish the lecture from the other day. So we're actually going to start a little bit where we left off, but just with a quick review. So we're talking about Pascal and Bernoulli in this, and then at the end, I've got, we're going to review an old exam problem. Okay, so here we go. For your review, what I want you to think about is this, okay? So we're looking at what I call the ice cube problem, okay? So I have a glass of water, there are some ice cubes floating in it, and what I want to know is, as the ice melts, what's going to happen to the level of the water in the glass, right? Right now it's right here, but as this ice melts, is that level, is it going to go up? Is it going to go down? Is it going to stay the same? Take a second and think about what you think is going to happen and why you think it's going to happen. Pretend these bubbles aren't there. But just this, as the ice melts, what's going to happen to that level of water? What do you think it is? And then I'll give you a second to think about it. Okay, so let's pretend that you paused and that you thought about it. Now, believe it or not, as the ice melts, the water level isn't going to change. It's going to stay the same the whole time, okay? And let me see if I can explain why, right? Buoyancy has the answer to this. So, I mean, first, as we think about this, right, the ice is floating because the frozen water is less dense than the liquid water around it, right? So it floats a little bit, right? And so what the water is doing is, in order for it to float, the ice must be displacing its own weight in water, okay? So that's why, I mean, if I pulled the ice cubes out and didn't let them melt, right, the water level would drop, right? But we have the ice cubes in there. But anyways, so now here we go, okay? So let's think about this. I have my glass, and it's full of water, and I'm going to take this giant ice cube that is 5 pounds for some reason. I don't know why anyone needs a 5-pound ice cube, but there it is. So that must be like a bucket. So we're going to put this in there, right? And it's going to float, but because that was filled to the brim, a whole bunch of water is going to spill out, right? A whole bunch of water is going to spill out. So now I have this water all over the floor, okay? So I guess the first question we could ask is, well, what is the weight of the water on the floor? And you know that in order to get that ice cube to float, it needs to displace a weight of fluid equal to its own weight. So there must be, bless this force diagram, there must be, right, the buoyant force is 5 pounds. There must be 5 pounds of water spilled onto the floor, right? Because if the weight of the ice is 5 pounds down and it's floating, so the buoyant force must be 5 pounds, and we know that the buoyant force is equal to the weight of the water displaced. So I've got 5 pounds of water sitting on the table, okay? And so now I take the ice cube and I pull it up, okay? I take the ice cube and I pull it up, and let's pretend that somehow none of it melted while it was sitting there in the water. I still have 5 pounds of ice. Okay, and the water level drops down, okay? Now, if I stand there all day and hold this 5-pound block of ice and it melts, it's going to drip back into the bucket. Well, this is 5 pounds of water. Well, it will be when it melts. And this is 5 pounds. Where's the water level going to go, right? It's going to melt, and it's going to fill it back up to the top, right? I mean, that's pretty cool. That's pretty cool. So in other words, you put a bunch of ice into, you fill your cup up with water and you leave a little bit of room because you know when you put the ice in, the water level is going to rise. Well, that water level isn't going to change as the ice melts, right? It's going to stay the same. And we can use buoyancy to think about that. I'll let you ponder that. You can even test it out, right? Go to the kitchen, get a glass, put some water in there, chuck some ice in it, use a Sharpie to mark the side of the, well, maybe not a Sharpie, but use something to mark the side of the glass. And watch the water melt, and I promise you it won't change unless it's super hot in your room and you evaporate a bunch, but that's probably not going to happen. Anyways, well, I guess it couldn't happen because if there's ice in it, then that water is going to be really cold and it shouldn't evaporate. Anyways, okay, so Pascal and Bernoulli. Okay, so we're going to start with Pascal. So here's the scenario, okay? We're looking at this lake. And this lake has this underground cave, and it's all full of water, and it's really marvelous, okay? But we're looking at this, and my first question is, well, what's the pressure of the water at the top, right? I'm standing here looking at this lake. What's the pressure of the water at the top? Well, you know that, well, it's got to be equal to the pressure of the atmosphere, right? That water's not going anywhere. So the pressure at the top is the same as the pressure at the atmosphere. And so my next question then is, if I go 10.3 meters down, right, to here, well, what's the pressure of the water down there? And we know from a couple days ago when we talked about depth in fluids, especially in water, right? A column of water that's 10.3 meters tall, the pressure at the bottom of that water is going to be equal to the atmosphere. So if I'm at 1 atm here, then down here, well, I just add another atm. So now I'm at 2 atmospheres, okay? Because I'm adding another atmosphere's worth of weight of pressure. So now I'm at 2 atmospheres here. Okay, that's okay. But now the real question is what about a point over here? Okay. What is, right? It's at the same level. It's at the same level at this point. What is the pressure here? Okay. And so now there's all kinds of things we can think about, right? You may be saying, well, I've got a ton of water on top of this. That's what's making an additional atmosphere of pressure right here. But I don't have quite as much water right here, so it must be less pressure. Okay, well, don't fall into that trap. Okay, it's not. Okay, let's move down. What if I go down here and I'm looking right here? Right, if I go down another 10.3 meters, right, it's going to be 3 atmospheres down here. And if I scoot over it, well, it's still 3 atmospheres, still 3 atmospheres, still 3 atmospheres. And then now I'm here. Is all of a sudden now it's less than 3 atmospheres? Like the pressure changes because I'm underneath this little cliff? Well, of course it doesn't, right? The pressure in this water is pushing in all directions at a time. So it's 3 atmospheres everywhere over here. And then as I start moving up, if I go up 10.3 meters, well, now I'm back to 2 atmospheres. Right? I mean, that's what's going on here, right? Now I'm back to 2 atmospheres. And anyways, but this is what Pascal is talking about, right? Is that the fluid in all of this is contained, right? There's no other access to air here. All of this is a contained fluid. So as long as I'm, this cave could go around and snake all over the place. It doesn't matter. As long as it's contained, then the pressure in the fluid is going to be the same at any level, measured from the opening, right? Measured from the surface, okay? Okay, so new situation, new scenario here. Some big asteroid, some big meteor comes and strikes and sends a shock wave across, right? Let's say the shock wave increases the pressure of the atmosphere to 5 psi. Okay, 5 psi here. Well, now what's the pressure down here? Well, 5 plus 1. I'm still just adding 1 atmosphere's worth of water weight. So now I'm at 6 psi here. Well, that means I'm at 6 psi here, right? That pressure, that shock wave, it added here, and then I added 1 here, and it adds that. I'm adding that. I guess I'm adding 4, right? So 1 plus 4 is 5. I'm adding 4 pressure everywhere in the system, right? So if I come down here, 1 more, right? It'd be 7 down here, right? But this is what Pascal's talking about. Okay, now do I need a giant asteroid to increase the pressure like that? No, I could have a gigantic plunger that I stick on top of this, and I could push down on the surface of the lake everywhere, right? I could add pressure, right? So if I push down with 1 atmosphere, if I push down with 1 atmosphere of pressure, this would go to 3, and that would be 3 as well, right? Because it's at the same level, right? The bottom down here, 10 more meters down. So if this is 3, then this would be 4, right? So. But this is what Pascal's talking about, okay? So here's Pascal. It looks a little bit like Snape. But anyways, he said this, right? Any change in pressure applied to an enclosed fluid, right? So it's enclosed. Think about like water in a bottle. Like if you have water standing in a dish, like that's not really enclosed, right? Unless I seal off the top with a big plunger, right? But any change in pressure that's applied to an enclosed fluid, that pressure is transmitted undiminished to all parts of the fluid and the enclosing walls, right? It's transferred equally everywhere. So like imagine, right, you have a balloon full of water in your hands, right? That's an enclosed fluid. If you squeeze on the outside of that balloon, that pressure's transferred equally everywhere, and you know that the balloon like bulges all over the place, right? Because that pressure that you're applying with your hand is applied everywhere inside the fluid, okay? So here we go. So what does this lead us to? Oh, well, it kind of brings us to these systems like a hydraulic system, right? Where I've got a little plunger here, so I've got this, I can push on this fluid here, and any pressure that I increase is going to be applied on this side, right? I get the same amount of pressure on that side. So think about this, right? If I lined you up and if I had, one student on this side and another student over here, okay, if if student A pushes on the small side with let's just say 1 unit of pressure, what pressure is student B going to feel over here? Well, they're going to feel 1 unit of pressure, right? It's going to be the same, okay? And so they'd need to push back with 1 unit of pressure, okay? If this student pushed with 5 units of pressure, this student would also need to push with 5 units of pressure to stay the same. Now notice I'm talking about this in terms of units of pressure, but do we push with pressure? No, we push with a force, right? So if we change this into forces, okay, if you think about this, right, the area over here is small, right? So I have a smaller area, so I apply same pressure, little force, little area. It gives me big area needs a big force. So I mean, think about this, and we'll run a demo of this in class. But on this little area side, I don't have to give very much force to create a pressure. That pressure is recreated over here on side 2, and now that's going to produce a big force because the area is so much larger. Okay. So we take advantage of this all the time, right? This is a hydraulic system, and this is everywhere. Like your brakes are hydraulic. We lift things with hydraulic lifts, right? And essentially what I'm saying is I have a little area over here and some fluid. Now, typically we use an oil instead of water because I don't want the pipes to rust. But if I apply a force here on this little area, it's going to create a pressure. That same pressure is going to be created over here. But because this area is so much bigger, that same pressure gives me a much larger force. So I can do things that I normally wouldn't be able to do, right? So little force, little area, same pressure, right? Big area, big force. So the question is am I getting something for nothing, right? How am I turning a little force into a big force? I'll let you think about that for a second. Well, there's a trade-off, isn't there? There's always a trade-off, okay? Because what's going to happen is this little area, little force, is going to have to travel. Let me go back. This is going to have to travel a really big distance. Yes, I'm using a small force and getting a big force over here, but this would have to move. So, for example, if the area ratios, if this was twice the area, if this area was twice as big as this, okay, I'd be getting twice the force, but I'd also have to move this plunger twice as far to get this one to move. 1 unit of whatever distance that is, right? So there is a trade-off here. I'm trading as look, I may not be able to apply a big enough force to pick up a car by myself, but I can apply a little force and multiply that force 100 times, right? If this area is 100 times bigger than this area, then I can multiply the force by 100 times. So now I can pick up a car. But my trade-off is I'm going to have to move this side. The distance I'm going to have to move it is going to be huge compared to the distance that this side will move, right? So excuse me, there is no free lunch here. Now, just looking at this diagram, by the way, if these are my starting points, if this is point 1 and point 2, right, here's this beautiful pressure formula that we developed in class a couple days ago, right? So the pressure, so without pushing on anything, let's pretend I'm not pushing on anything, right? The pressure at place 2, right? So here's position 2. So here's position 2 is going to be equal to the pressure at position 1 plus rho GH, right? Plus, and here's the H, right? So the pressure here right now, this is already at a higher pressure than this because it's deeper in the fluid, right? And we just barely talked about this, right? It's deeper in the fluid, okay? But Now as I add pressure to here, right, as I make P1 bigger and bigger and bigger, right, I'm always just going to be adding this rho GH to it, but as I add P1 here, P2 is going to grow. And then I've given it a little bit of extra nudge by making this really long, right, so that this is deep. Anyways, so that's, applying a little bit of Pascal to some of this pressure stuff we're talking about. Okay, shifting topics just a teeny bit, okay? So, okay, now this is a weird scenario, but just bear with me, okay? So pretend you've got like a stick Captain Picard and a stick first command. It was either for, I don't know what it was. Stick Spock over here, and pretend that they're both on top of some big canyon, and they're looking down into this canyon. And now notice that my canyon starts pretty wide, and then it narrows, and then it's pretty narrow over here where Spock is. Okay, and people, I don't know, maybe there's some city that's over here that's burning. I don't know what's going on. But people they're fleeing, right? They're running into this canyon. Okay. They're running into this canyon. So I've got a whole bunch of people. But notice, let's assume that I'm adding 5 people per second are entering the canyon, right? So over here, 5 people per second are continuously coming into the canyon. Well, what's that going to mean as the area of the canyon shrinks down? Right? What's going to happen to these people over here? Okay? If these folks are counting people, Picard's going to be counting, okay, well, I'm seeing 5 people per second come in. Guess what Stick Spock has to see? If I'm cramming 5 people per second into this side, well, Stick Spock must also be seeing 5 people per second run by here. Because if not, then these folks are going to get all compressed and squished in here, and nobody wants that, right? So what must they be doing? Well, they must be speeding up. Right? They're coming in slowly, but then they realized, wow, it's getting crowded. I've got to speed up if we're going to maintain this same rate. So these people are going much faster than these people, okay? Much faster. and okay, so now, yeah, so little speed, big speed, in order to keep that rate the same, okay? In order to keep the rate the same. Now, we're not dealing with people, we're dealing with fluids, right? And so the cool thing, now I guess people are kind of compressible until, you get them all huddled next to it. Anyways, but fluids aren't, right? Fluids, we say that fluids are not compressed. So I've got a fluid in here. I can't compress the fluid. So if I have a continuous rate of fluid coming into my pipe and the pipe shrinks down, well, that same rate of fluid must be going through over here. So the only way, if I'm getting 5 liters per second over here, I've got to have 5 liters per second moving over here. And the only way for that to be possible in a smaller area is if it speeds up. If it speeds up. Okay, so I'm going from a small velocity to a big velocity. Okay. So if I have this kind of reddish-orange ball right here in the middle, and if I'm tracking on this one, right, if I'm going from a low velocity to a high velocity, what is that reddish-orange ball doing? It must be accelerating. It has to be. If you're going from low velocity to high velocity, it must be accelerating, which means that the force over here must be bigger than the force over here because I'm speeding up into the narrow gap. Okay, I'm speeding up into the narrow gap. The acceleration is this way. I'm speeding up into the narrow gap. So the pressure has to be higher over here, right? If the direction of the acceleration is to the right, then I must be at a higher pressure here and a lower pressure here, right? So all this crazy canyon story is to bring us to this realization that if I'm going to take this fluid that can't compress and squeeze it into a smaller area, that means that over here where it's moving slowly, the pressure is high, and that high pressure accelerates the fluid over here. And so now once it's sped up, the pressure's got to be low, right? If this pressure was high too, then I'd have an equal force and this couldn't speed up, right? So I have to be going from a high pressure to a low pressure, okay? And this, right, the Bernoulli's work lives in this idea that fluids at lower velocities are at higher pressures, okay? The secret of lift and flight and all of these things lives in this idea, okay? And we'll talk about it. All right, so there's Bernoulli. What a guy. And essentially, he developed this equation, right? He said, look, if I look at a place, so I've got this weird little looking fluid pipe here. If I look at a place here in the pipe, and I take the pressure plus 1/2 the density of the fluid times the velocity of the fluid squared, and by the way, the units of this end up being a Pascal. Isn't that cool? Pascal plus Pascal. And I can also think about this in terms of height. So plus rho GH, right? The height of this fluid from some reference point. This gives me kind of like a pressure profile for the fluid. And that's going to be equal to a constant inside this contained fluid. So, then when I look over here, notice I'm at a new height and a new area. There's so many cool things going on here. But what I want you to look at this and see is, this should look really familiar to you, friends. You should be looking at this and be like, oh, this looks a little bit like kinetic energy. Instead of 1/2 mv squared, I have 1/2 rho v squared. And this looks a little bit like gravitational potential energy. But instead of mgh, I have rho gh, right? But what these three things do it kind of gives me, right? This P, here's the external pressure being applied on this side, the speed of the fluid, the height of the fluid. It's going to give me a profile of the pressure of the fluid at this point. And that's going to be a constant throughout this thing. Over here, I've changed H. So if I've changed H and it has to be a constant, then V has to change too, right? There's so many things that are changing. Anyways, now, here's the good thing, class. I'm not going to make you plug numbers into this, but I do want you to use this equation to think. Okay, so here we go. So here's a pipe, kind of similar to the pipe we were looking at before. And let's say I have fluid flowing through this pipe. I want to look at it at two places. Here's position 1, here's position 2. Now notice the middles of the pipe here and here, those are basically the same. So what is that going to do, right? So here's my equation. I'm at position 1, position 2. If I'm at this basically the same height, now I know I made the areas bigger. If I'm at the same height, well, that's just going to subtract out, right? That's just going to subtract out, and so I'm just left with this, that the pressure at position 1 plus 1/2 rho v1 squared is going to be equal to the pressure at position 2 plus 1/2 rho v2 squared, okay? But from the previous slide, you know that if I'm going to have, so for example, like a question I could be asking you is, well, how does the pressure here compare to the pressure here, right? How does the pressure at 2 compare to the pressure at 1? And you guys can tell me, that, it's got to be going slower here, right? Because when I get into this smaller area, it's got to speed up, right? So it's going slow, it speeds up into here, right? Because I've got to have the same rate. So if I'm going to force the same volume of fluid through this little space, it has to be going faster. But then I get into this big space again, and it can slow down again, right? So high velocity. So if this V is big, and this V over here is small, well, what does that tell you about the pressures? Well, it tells you that this pressure must be big compared to the pressure here, right? So this is just another way to think about this. Is you have another tool you can use to think about these things. Now, most of the Bernoulli stuff, we're not going to worry about the height piece of it. We just want to think about what does the speed of the fluid do to pressure, okay? And what I want you all to, the takeaway here is that small speeds correlate with high pressures. High speeds correlate with low pressures, okay? We're going to do a bunch of demos in class to kind of showcase this so you can see this, but that's what's going on here, right? We've done some thought experiments in the slides, but that's what's going on here. All right. Woo! Look, the monkey and the snake again. One last little thing is Okay, there's my Bernoulli equation. Ugh. Now look, if I'm comparing, if this is place 1 and this is place 2, right? So here's go to 1 and here's go to 2. Okay. Is the water in this lake moving? And you're going to say, well, of course it's not. Okay. So I can dump the velocity bits. Now I'm down to just this, that the pressure 1 plus rho GH1 is equal to, okay, now what's this? Let's subtract rho GH2 over here. Now notice I've got a rho G. I can pull those out, and I've got an H1 minus H2. So that gives me this change in H. So in other words, the pressure down here at 2 is equal to the pressure at 1 plus rho GH. Whoa! We've seen this thing before, right? That the pressure equation that we developed 2 days ago has been hiding inside of Bernoulli's equation the entire time, right? So, right, this is a second, we'll call it a witness. A second witness, right? It's a second witness or example that this is the case and that this equation works. I think that's pretty cool. All right. Last little Bernoulli example here. How many of you have seen, like, hauling down the highways, these trucks that have these tarpaulins on? I'm just going to call it a tarp. They've got these tarps on them, right? And if this thing is parked, let's say that there's like 10,000 potatoes in here. And if this thing is parked, you know, we put the tarp over it because we don't want the potatoes to come rocking out of here if you hit any bumps, okay? Well, okay, while it's parked, what's the velocity of the air that's inside the trailer bed? Well, that velocity is, well, it's 0. I mean, it's not moving. It's just, you know, it's just and if it's not moving, then the air up here is not moving relative to the tarp, so the pressures on either side are the same. So this thing is flat. But what happens when the truck starts to drive? Well, as this truck starts to move forward, the movement of the air inside of the truck bed, it's just kind of still sitting there. I mean, the potatoes, like, relative to the top of the tarp, the air is just still sitting there. But all of the air out here is moving super fast now relative to the truck. And that super fast moving air, what's the pressure going to do? Well, it's going to go down, of course. So the slow moving air inside of here, you'll have a high pressure. It's going to push up on here. And so next time you're driving down the highway and you see one of these things go by, if you look, you'll notice that while the truck is moving, this is bowed up, right? And it's because of Bernoulli, right? The fast-moving air on top, at least, as the truck's moving through the air, that air is moving really fast relative to the tarp. That creates a low-pressure system, and so the high pressure in here is going to push up on the tarp, right? You can see this stuff everywhere, okay? You can see this stuff everywhere. All right. Excuse me. Last thing for this little video is this. I want to run through one of those example problems. So here it is. So George, the curious little monkey, has found a coconut and a big potato. He knows they weigh the same because he has placed them on a crude balance, but they are definitely different sizes. Okay, so different volumes. But he knows they weigh the same because they balance. By the way, so I asked Copilot to give me a picture of Curious George, and it told me that it couldn't because that's copyrighted material. But then it asked, would you like me to create a picture of a monkey that happens to be curious? And I said, yes. Could I have a picture of a monkey that looks curious that is holding a hat? And it made me this picture, which I guess is not a picture of Curious George holding a hat. Anyways, so George takes them off the balance, and for some reason, he places them both in a freshwater lake. The density of fresh water is 1 gram per cubic centimeter. The potato sinks in the water and displaces 300 centimeters cubed. Right, that's the volume that the potato displaces. The coconut floats in the water with exactly 2/3 of it submerged and displaces 480 centimeters cubed of the water. Okay, so floating coconut, 2/3 down here, 1/3 up here, sunk potato. And now this thing says, well, what's the mass of the potato? Woo! Okay. Now, this is an example of an old exam question. So let's kind of like lay out some of the stuff we know. Well, we know that the coconut and the potato weigh the same, right? Weight of the potato is equal to weight of the coconut. We know that from over here. okay? And I know that mass is hiding inside of weight. Well, I also know that the coconut is floating, so that must mean that the weight of the water being displaced by the coconut must be equal to the buoyant force. And so if I were to draw a force diagram for this floating coconut, right, the buoyant force is going to be equal to the weight of the coconut. So if I can figure out what the buoyant force is, then I'll have the weight of the coconut. And if I have the weight of the coconut, I have the weight of the potato. So all I need to do is figure out the buoyant force. And we know that our basic definition of buoyant force is that it's the weight of the fluid displaced, right? Or it's the weight of the fluid in the Casper box, right? And this is going to be like a Casper half coconut, or I guess 2/3 coconut. But it tells me right here that the coconut is displacing 480 cubic centimeters of water, okay? And so here we go. So the buoyant force is going to be equal to the density of the fluid times G times the volume of fluid being displaced, which is also good, equal to the weight of the coconut because the forces are balanced. Okay, so density of 1 gram per cubic centimeter, and I've got, so here's the volume of fluid displaced, 480 centimeters cubed, times 10 newtons per kilogram. Now, this should cause you to pause, right? You're looking at this, and in class, this is where some of you have asked me about unit conversion, right? And you need to be careful of your units. That's why we're listing them all out here, okay? If I look at this, I know that this centimeters cubed is going to cancel with this one down here, right? So if I were to multiply these two terms together, it would leave me with just grams, okay? And then I'd bring my gram over here. Well, my gram isn't going to cancel with a kilogram. So that's why I'm doing this little conversion right here. I'm going to, 1 kilogram is the same as 1,000 grams, right? Those are the same things. So this is like multiplying by 1. So my grams are going to divide out. So I've got gram on top, gram on bottom. Those are going to divide out. Kilogram on top, kilogram on bottom. Those are going to divide out. The only unit that survives is the Newton, okay? And luckily, that is the unit for weight, right? So I'm exactly where I need to be, okay? So 1 times 480 times 10 times 1 over 1,000, or dividing by 1,000, and that's going to leave me with 4.8 newtons, which is the weight of the coconut, which is also the weight of the potato. So now I have the weight of the potato, but I know that weight, so this 4.8 is equal to mass times the acceleration of gravity, which is a Newton per kilogram. So I divide this over, the newtons canceled out, kilogram flips up to the top, and I have that my potato has a mass of 0.48 kilograms, or 480 grams. Okay? That was a lot of work thinking about this. And by the way, hopefully you're pausing the video as you're going through. Now, of course, I'm not only going to ask what the mass of the potato is, right? So I could say, well, what is the density of the potato then, right? And so density is just mass over volume. I have the mass now, right? I found the mass of the potato. Do I have the potato's volume? Well, I know that the potato is displacing 300 centimeters cubed of water. So yeah, it displaces its own volume. So I've got the mass, I've got the volume. So I've got 0.48 kilograms over 300 centimeters cubed. Now that would be a weird density unit, kilograms per centimeters cubed. Normally we do grams per cubic centimeter. So I'm just going to convert those kilograms into grams by multiplying by, 1 kilogram over 1,000 grams. And this leaves me with a density of the potato of 1.6 gram per cubic centimeter. And this makes sense. It's more dense than the water. That's why it sinks in the water. Boom. Got it. Made sense. And I have the density of the potato. I don't know why I need that, but I have it. Okay. So then the obvious next question is, well, then what must be the density of the coconut? Okay. So here's my floating coconut. And I know that 2/3 is underneath and 1/3 is on top. And I know this coconut's floating, so it must be less dense than the water, right? This is going to give me a tell on the answer that I eventually find here. So I go to my density equation. It's mass over volume. The coconut and the potato weigh the same, so they must have the same mass, right? So I have 0.48 kilograms of coconut. But what's the volume of the coconut? I know it's displacing 480 cubic centimeters, right? But that's only 2/3 of its volume. Okay, so I need to work with this. Here we go. So one way to think about this is, the weight of the coconut is 4.8. That's the buoyant force. So, and the buoyant force is also equal to the weight of the fluid displaced. So I'm down here. So I'm 4.8 newtons is equal to the mass of the fluid times g, right? Because that's the weight of the fluid displaced. So the mass of the fluid being displaced is 0.48 kilograms. And I know that the density of the fluid is 1 gram per cubic centimeter. So if I solve for the volume here, right, because density is mass over volume, I can find the volume of fluid displaced to be 480 cubic centimeters. But I already knew that because it tells me that right here. But we just went through that because we could and it was fun. So I've got this volume that's being displaced. Now, this 480 cubic centimeters. That's 2/3 of the volume of the total coconut. So if I multiply this by 3/2, I'll have the full volume, okay? And so the full volume of the coconut is going to be 720 cubic centimeters, okay? Now I can bring that back over here. So 0.48 kilograms over 720 cubic centimeters. Again, I need this in grams per cubic centimeter, so I divide the kilograms out. I'm left with grams per cubic centimeter, and boom. So the density of the coconut is 0.67 grams per cubic centimeter. And that's less than water, so I have a really good feeling that this is going to be right. Okay, so what is the buoyancy force by the water on the coconut? Is that greater, less than, or equal to the buoyant force by the water on the potato? Now, don't fall into the trap, my friends. You may say, oh, the potato sunk, so all of its volume is down there, so it must have a greater buoyant force. Or some of you will think, oh, well, the coconut's floating, so it has the greater buoyant force. You can't use that logic, right? The only you can tell what the buoyant force is by looking at, well, what is the weight of the fluid being displaced, right? And it tells us right here. The potato is displacing 300 cubic centimeters. The coconut is displacing 480 cubic centimeters. Which one of those weighs more? Well, the coconut is displacing more water, so it must then have the greater buoyant force, not because it's floating, but because it's displacing more water than the other thing. That's why. Okay, that's why. Be careful. All right. Oh, shoot, I didn't disappear my things here. Oh, so the first question says, draw a free body diagram, right? So George, curious George, he takes his coconut and he pushes it under the water. Okay, so we're forgetting about the potato. He pushes it and he's holding it under the water and it says, all right, draw a free body diagram for it totally submerged, right? So I've got the dot, I've got the weight, what's touching it, the hand. So I've got a normal force from the hand, I have the weight from the force of gravity from the earth, I've got the normal force of George's hand, and balancing that is the buoyant force. But now this is much bigger than what I calculated before because I have all of the volume submerged, right? So I've got all this stuff going on here. Okay. And that leads me to over here. The last question is right now the weight plus the normal force is equal to the buoyant force because it's in static equilibrium. But if George stops pushing, the coconut's going to want to shoot upwards, right? So what is the magnitude of its acceleration just after being released? And yes, you can already see the work. My apologies for that. But if I eliminate this normal force, I'm going to apply Newton's second law, right? And so if I say that up is positive, then the buoyant force minus the weight, and I like to say that the direction it's going to accelerate is positive. So the buoyant force minus the weight is going to equal ma. And I don't know what the buoyant force is anymore because now the full volume is displacing water. But I do know what the thing weighs, right? It's the same as the potato. It weighs 4.8 newtons, okay? So, and the mass of the thing is 0.48 kilograms times A. So I need to figure out the buoyant force, and that's what this is doing over here. And of course, the buoyant force is just equal to the weight of the fluid being displaced, which is its density times its volume times G. So I've got the density of the fluid, 1 gram per cubic centimeter. It's water. It's in the water. Not the density of the coconut, but the density of the fluid, times the volume of fluid being displaced, 720 cubic centimeters, times G, 10 newtons per kilograms. And again, as you're looking at this, grams and kilograms don't cancel, so I've got to convert the kilograms. I've got to convert these grams into kilograms. Oops, that's what I'm doing here with this little conversion so that my units work out. And it leaves me with a unit of newtons. When I multiply this all out and divide by the 1,000, you get 7.2 newtons, which I would then bring back over here. So now 7.2 Newton buoyant force minus 4.8 Newton weight is going to be equal to ma. Divide the mass over, and I've got an acceleration of the coconut that's upward going 5 meters per second squared. Now this just asks for the magnitude. So if you'd gotten a negative acceleration because let's say you said that down was positive, we'd still just put in 5 anyways because it's only looking for the magnitude, okay? Anyways, one of the things to be careful about in these problems is your units, right? Because I've got grams and centimeters, but I've got newtons and kilograms. Make sure you're converting, okay? So that your units match and flush out, okay? Awesome. Okay, that's it for today. That's it for this video. Hope you're having a marvelous weekend, and I'll see you in class next week. If I knew how to stop the video. End show.